And we're back. Welcome back from the weekend. Today we will change gears with material from Chapter 3 on processes. Before we begin, a few administrative bits. The reading has changed or has added on by the 6th of October. Please make sure you are reading through sections 3.1 through 3.8. That's page 106 through 145 in the OS Concepts book. The previous reading assignment, and it's all on the Blackboard for the course, the Blackboard site, is due by the 24th. This is not a lot of reading if you space your time out and do a little bit, 1 hour every day. So we run lots of applications on our systems, and these applications can be local, but more recently, these applications these days are distributed. They're remote applications, but these applications are still delivered to our machine, and we're able to get things done or entertain ourselves or go shopping with them. And so the objective for Chapter 3 is to talk about processes or programs in execution. And this is really the basis of your being able to get things done computationally. It'll talk about features of processes, their scheduling, creation, and the communication between processes. Now, this communication is particularly important in so-called distributed applications where you have your computations scattered among different machines interconnected through the network. We'll also look at inter-process communication and the various ways of doing that, and we'll talk about structuring these distributed programs a little bit as client-server systems. So why don't we begin? So what is a process? It all started with batch systems, and in batch systems, the nomenclature was called a job, and a job was nothing more than some program that a user desired to execute. And so you would submit this job to the system, and it would take all of these jobs, line them up, and execute them one after the other after another. Now, this led into timeshare systems where these jobs were switched, giving the illusion that a number of users from terminals had usage of that computer. So to you, it appeared as if you had exclusive usage of the machine, but you really had fractional usage. And it was called time sharing because the systems would switch between each program, giving each a fraction of time on the CPU for this big, powerful machine. And so these user programs were called tasks, and time sharing brought in or ushered in this idea of switching between these programs in their executable state. Now, in the book, job and process, they're synonyms. They're used, for the most part, interchangeably. And a process is defined as a program in its executable state. That's really important, its executable state. And when a process executes, if you think about what it means to write a program, you might have a statement like A equals 1, B equals 3, C equals A plus B, and maybe D is equal to 1.5 times C, for example. So what happens? You execute the first line, execute the next statement, execute the next statement, execute the next statement. So this thing that we've been calling an instruction stream is just a set or stream of operations that are executed onto the CPU. So if you think about it, you have your CPU, and you have all the components that comprise the CPU, which I will not outline. So first, this instruction is set up on the CPU and executed. Then next, this instruction is set up and executed. Next one, and so forth. So this stream of instructions that I've been calling an instruction stream is the executable form of your program. So process proceeds in our sequential fashion as this instruction stream is executed on the CPU. And so it's really important to make this distinction that it's only just a program when it's sitting on disk, but it only becomes a process when its instruction stream is actively being executed, and this is done in a sequential fashion. And so a program, a process, is comprised of a lot of different parts, and these parts have names. For one, we have the program code or the text section. Now, the text corresponds to the actual program statements. That would be your A is equal to 1, your B is equal to 3, your C is equal to A plus B, and so forth. Now, this text of your program, the actual instructions stream of which is executed, that exists in one part of your program, and that's called the text section. And whenever the CPU identifies the next instruction it's going to load and set up, well, it's numbered. And it's numbered based on the beginning of your program, which labels it as perhaps the 0 statement. The next one is going to be the first statement, then the second statement, third statement, and so forth. Well, there's a register that maintains the offset or the address, as it were, of the next available executable instruction. And why is that? Because if the CPU is going to load each of these instructions and set them up to execute, it needs to know where to load them from. And that where to load it from is described by the so-called program counter. And it's a register in the CPU, the PC or program counter, and it identifies the address or location where the next instruction is going to be loaded, from which the next instruction will be loaded. Then we also have the stack portion of a process, and the stack is used for temporary data. It implements a stack data structure, and this is used for multiple purposes. One is for function parameters. So when you call a function foo, and you give it a parameter int a and char b, for example, well, these parameters are pushed onto the stack. And then when you have also local variables like integer c is equal to 5 inside of that function, well, storage for this local variable is allocated by pushing onto the stack. And so the stack also handles return addresses. When you're done with your function and you exit, and let's say you said z is equal to the result of calling foo on 5, comma, the character a. Okay, well, when that return happens, when you call the function, you're actually changing the program counter to go to the definition of some function in your code called foo. And then when you are done with that function, you need to know where to go back in your execution, in your instruction stream. And so this idea of where to go back is just the location associated with the next instruction right after your function call. And that location is stored on the stack. So the first thing that happens, you're executing your program, you call a function foo. There's a definition for function foo down below. The program counter knows, in this case, instruction 4 is the call for foo, and let's say the next instruction, 5, was here. So before actually switching to that location for the function foo, it's going to remember that 5. And where does it remember it? By allocating it on the stack. So when the function is done executing, it says, okay, well, let me pop the stack in order to retrieve that address associated with where that location in your program where execution will continue. And so the stack stores a lot of different types of temporary data, function parameters, return addresses, and local variables. And this is all managed for you. You don't have to do a thing. Simply by writing your code, the compiler, when it compiles your program, one of the things it does is manages that piece of memory that implements a stack, and it pushes values onto the stack when it allocates, and it pops values off of the stack when it deallocates, and also when it retrieves these values. And so this is a type of automatic storage. You don't have to do anything for this. There's also a section called the data section. This is where your global variables exist. So suppose you have a program. Here's your program. And your program consists of a function, f1, and let's say it consists of another function, f2. These functions are defined, and they also have local variables. Those variables only exist within those functions. Okay, well, sometimes you want to define a variable. It's a so-called global variable, like int number equals 7. You might want to use this variable everywhere in your program. And such a variable is called a global variable. Global meaning that every function, every statement can actually see and use this particular variable. And so the data section of your program consists of all the global variables. And when you compile your program, the compiler sets up or establishes different sections of your program that have different purposes. One such section is the data section containing all the global variables. Okay, and then lastly, we have the heap. The heap is your pool of memory, and unlike the stack, this is not automatic storage. You have to do everything in order to allocate and deallocate storage space out of this heap. Now, this is for so-called dynamically allocated memory. It's allocated during runtime, so that means there are special statements, and these statements for C are called malloc and free, and these statements will actually allocate space for you dynamically. So programmatically, you can actually set aside memory from RAM, and you can also return the use of that memory for anyone else to be available for any other process that might want to allocate memory. Now, this region of memory has a name. It's called the heap, and the heap is the other part of your process. So a process consists of a text section, a program counter, a stack, data section, as well as a heap, which is dynamically allocated memory. A program itself is passive. A program is what is on disk. So let's say you have your disk here, and you write some function, let's call it main, and it's an executable. It exists on the disk. It is a program. Remember, a process is active. It's something that is actively executing on the processor. And a program becomes a process when this code, text, data, etc., is now loaded into memory and put in the status where it can start to be executed, the instruction stream executed on the CPU. And so how do you start your programs? In a whole host of ways. You click on it. If it's a WIMP interface, window icon menu pointer, graphical user interface, you click your mouse on an icon, and that launches a program that's taking it off of disk, causing it to be loaded into memory, and then it is scheduled for execution, fractional use of the CPU's time. It can also be done on the command line, as is the case with a terminal on a Unix-based operating system like Ubuntu Linux. Now, one program can actually exist several times in memory. So let's say you have your main program. Okay, here's main on disk, and here's memory. You click on it once, it loads, it's a process running. I'll call it main prime, the running version. You click on it again, it loads it the second time. It's running in memory again, main prime. Now, here, you can have multiple copies of the same program executing, for example, in a multi-user system if more than one person is running it. So let's say you and I both have an account on the same machine. You decide to run Spotify. I decide to run Spotify. We're both running Spotify. Two copies of Spotify program is in memory. One of them is owned by you, and the other copy is being run by me. So you can absolutely have one program exist as several processes because you can have different instances of this active entity, this program in execution, being scheduled on the CPU. Okay, so this is an example, a schematic, it's in the book, of the different parts of a program and what the relationship are between them as it exists once the program or process is instantiated or loaded into memory. So here we have the text section that contains our instructions, our instruction stream. You have the data. These are global variables. you have the stack, and the stack is going to grow in one direction. As you push, the stack is going to get bigger. As you pop, the stack is going to get smaller. So the stack is automatically allocated for you and automatically managed. It's automatic storage. And the heap is carved out of memory, but that's manual. You have to allocate it yourself, dynamically allocate it through malloc and free in a language like C. And so the heap grows as you allocate new memory, it gets bigger. If you free memory, well, those pieces that you allocated are now available for others to use. Okay, so what happens in a heap also is that it's not necessarily contiguous. So if you allocated a piece of memory, and let's say you got this piece, and someone else came along and allocated another piece, someone else came along and allocated another piece, if you go ahead and you free your piece, there's now a hole in memory, right? You have parts of memory that are occupied, and you also have parts of memory that are available. So you can have holes in memory. It's not contiguous, unlike a stack, where a stack is contiguous, this automatic storage. All right, so a process has state associated, and the process state notes or describes what is happening to that process. And so a number of states exist, and the process will actually transition between states to indicate what that process is doing in the moment. And so a process, if it's in the new state, that means it's being created. There's a data structure that's allocated, a struct, and the structure is going to be that format in memory where you're going to store all of that information needed to describe the executable state of this process on the CPU. Because remember, we're going to switch between processes, sharing fractional usage of the CPU's time. And if you're going to switch between them, well, you need to write down what a process was doing when you switched so that you can reload that information later on and resume where the process left off. So the new state is that state where the process is being created. That's where it's brought into memory. And when it's brought into memory, it sets up that data structure in which the executable state of that process is written down so that you can switch between processes. Then we have the running state. That means it's currently executing its instruction stream. They're being scheduled on the CPU, and it's setting them up and performing them. Then there's the waiting state, meaning it's waiting the process for some event to occur. Now, of course, if you're waiting for an event to occur, you don't need time on the CPU because that's just wasteful. So when you're waiting, you get kicked off the processor until you're ready to be scheduled for execution, i.e., to actually set up and execute your instruction stream. So we have this wait state. We also have the ready state. That's a process that can execute on the CPU, but it's not executing on the CPU. So once you're done waiting, you are put in the ready queue, and every process that's in this list called the ready list, i.e., they have a ready state, that means if they are selected for execution on the CPU, they can actually execute on the CPU. So the ready state describes a process that's waiting to be assigned to a processor to actually have its instruction stream executed on the CPU or a set of CPUs. Then there's also the terminated state. That's a process whose execution is finished, and termination means that your resources, the data structure, is being freed up, and all of the resources that you acquired are being returned back for availability for usage by others on the operating system. So this is a diagram that's in the book, and it talks about the transitions between the different states of a process. So you start out, and your process is in the new state. That means you're being allocated. Everything's being set up, all the data structures and file loaded from disk into memory. And then you're admitted to the system. Now, admitted to the system means that you're added to a linked list, and that linked list is the so-called ready queue. And that ready queue consists of the data structure describing all the processes that could potentially be selected for execution of their instruction streams on the CPU. So one is selected, and that's called scheduler dispatch. There's a function in the operating system called the scheduler, a component of the OS, and the scheduler picks from the linked list, the ready queue, some process to then populate its state information onto the CPU and execute its instruction stream. So the scheduler dispatch occurs, and that process goes from ready, transitions, to running if it's selected for execution. So it goes ahead, it's running, and all of a sudden some event occurs or I/O operation, and it has to wait. So if it has to wait, it's kicked off the processor. Its information or state for its instruction stream execution is written into the data structure, and then it enters this waiting state. That's where it's waiting for that I/O to complete or some interrupt for I/O to complete. Typically, interrupt is a separate transition. And so once that I/O has completed, maybe it's waiting for a disk read to transfer its buffer full of information from the device controller for the disk to memory for that program. So once that I/O operation is complete, it's no longer waiting. It is shifted to the ready queue, and now it's available for execution again on the CPU. For the other transition, you're going from running, an interrupt occurs. Now, the interrupt could be because you executed a system call, and there's a special type of interrupt that is thrown when your fractional use of the CPU, that time, is up. And when that interrupt fires, you're taking off the processor, your information is written down in the data structure, and then you transition to ready, and you're available to be selected again for fractional usage of the CPU. And then lastly, when you're running, the process could exit. And what that exit does, it transitions you to the terminated state, and that means the process is being deallocated. All the data structure and other resources are being returned back for free availability to the other processes on the system. Data structures are deallocated, and your process is no longer executing. So what is this data structure? This data structure has a name, and it's called the Process Control Block, or PCB. Now, information associated with each process is stored in this data structure. It's a so-called C structure. It's also sometimes called a task control block. And this task control block has pieces of information such as the process state, whether it's ready, running, waiting, terminated, etc. It also has the program counter, which is the location or address of the next instruction to be executed. It includes contents of the CPU's registers, all of the register file for the CPU, because remember, it writes down that information from the CPU to a data structure so that it can then resume later. When it resumes later, so here we have the CPU, here we have process control block, the PCB. So when a program is going to execute, its information is loaded onto the CPU. When a program is no longer on the CPU, that current state of that program in executable state is written back to that PCB. So that information is sort of bookkeeping system that writes down the current status of the program in execution from the perspective of the CPU so that it can resume later where it left off. And so this schematic lists a bunch of that information to show you that this can be quite big. I'll actually show you, or take the time to show you, the actual task control block for Linux. So what else does it have? Scheduling information. Things like the priority associated with the scheduling, because some processes can be deemed on your system as more important than the others. Contains memory management information about all of the dynamically allocated memory on the heap that a process is associated with. Accounting information about the amount of time that this process spent executing on the CPU. That information is written down in the PCB, as well as the status of I/O devices that are allocated, things like files and network connections. Because if you have these resources and the process gets kicked off the CPU and it resumes, well, it has to know what connections do I have, what pieces of memory am I accessing that I've allocated. So this schematic depicts the interchange between two processes, T0 on the left-hand column and T1 on the right-hand column. We have the operating system in the middle, and at the outset, let's imagine that T0 is executing. T1 is currently idle, it's waiting. So P0 is executing, and all of a sudden, it executes a system call, does something like a file read. So what happens? Well, it's kicked off the CPU. So we have our CPU, executing, we have the PCB, process control block, for P0, and then we have the PCB, process control block, for process P1. So P0 is executing, so that means at some point in the past, its state information has been sent onto the CPU. So if it's no longer executing, well, what happens? If we get a system call interrupt, well, it gets kicked off the CPU. So that means whatever the current status is for P0, process P0 on the CPU, that information is written into its PCB, process control block. And then, all right, well, it switches to process P1. Scheduler selects process P1. So that means the state that's been saved away in the PCB, process control block for P1, is going to be loaded onto the processor. And then the instruction stream runs. Now, when the instruction stream is executed, of course, the program counter is going to change because it's no longer going to be the first instruction that's executed. It might be the third or the fourth, etc. So now what happens, that process P1 starts to execute after its state is loaded from its process control block, and now it starts executing. So then it triggers an interrupt or makes a system call, P0, P1 does, and that process repeats. So the status of P1 is then written into the process control block for P1, and then PCB for P0 is used to populate or load the state where process P0 left off on the CPU, and execution of P0 continues. And so this switching and loading and writing and switching and loading and writing continues again and again and again. And the result is the sharing of the CPU between two processes. Now, this only visualizes, and this is in the book, it visualizes two processes, but you can imagine 20, 30, 100 processes. It's the same thing that happens. So we've only talked about a single instruction stream, but processes can have more than one instruction stream, and we said an instruction stream corresponds to locations from which can be found the next instruction to execute. And it's the program counter that defines this. So that means if you want more than one instruction stream, you're going to have more than one program counter, because that corresponds to having more than one location that can execute at the same time. And the abstraction for this in an operating system is called a thread. So a process and its description, its PCB, is going to then have in it, among all the information included, a list of so-called thread control blocks. Now, these thread control blocks are similar to process control blocks, but instead of defining all of the information for a process, they only describe those pieces of information needed to describe the instruction stream itself, like the program counter, the stack pointer. And so the focus of Chapter 4 will go into detail into threading, but since a thread is a part of a process, it's important to at least discuss at a high level what is a thread. So this is a PCB representation in Linux. It's called a task struct, and this is the so-called C struct or C structure. And some of the information, not all of it, but included, is the process identifier. The state of the process, we talked about ready, running, terminated, waiting, etc. Well, it's in this variable called state, and its type is a long. A long is a type of integer, and it can be 64 bits in its representation. And so the time slice, that's the scheduling information about how much time it has on the processor. And then it also has a parent process. And you'll see here the star notation we talked about, the pointer to a task struct. So this task struct for a particular process, it is a node in a linked list implementing a list of processes. And this particular list, this pointer, refers back to the parent process. A parent process is a process that starts another process. That parent is called the parent because it waits for the termination status of each child process that it creates or it invokes. Okay, we also have a list that describes this process's children, because a process can create another process, can create another process. And then we also have a list of open files as well as memory management information through this other structure called memory management struct. Okay, so We have the currently executing process. We have the task structure or PCB for the current process that's executing. So now we select the next process to execute. It could be in a sequential fashion, going through the list of task structures, or it could be some other selection criteria that we'll talk about when we get more into process scheduling. But nonetheless, we have a current process control block corresponding to that process whose information is currently being executed on the CPU. So then when the CPU says, all right, your time is up, it takes the current status of that process and it writes it into the PCB, and then a new process is selected from on that list. Now, at the following link on this slide, you'll find the actual task structure for the process control block for Linux. And so what I'm going to do is I'm going to pop out of PowerPoint for a moment, and we're going to go into the task structure for Linux and actually show you what that looks like. So here we have that structure, and you'll see a bunch of types here, and the structure is nothing more. It's kind of like a class in Java, only there's no public or private in scope. Everything is global in scope or public in scope. And it's how you can aggregate a bunch of different data, including pointers, lists, and primitive data types as a single name or a single type. And it's a so-called user-defined type. A user-defined type is a structure, data structure, that has a bunch of components or fields, if you will, and each of these fields has a type, but you associate it and describe it under a single name. It's kind of like a class in Java, but it's not a class. So here, let me scroll down and let me find the task structure. Here's task struct. Now in task struct, we have a beginning and an end. So we have the declaration struct task, open close curly brace, and down below, close curly brace. Everything in between are all the pieces of information needed to describe a process. So this is the PCB, the task struct. And so if we look at it, well, we have pointers to task struct. These are the parent pointers for the structure. And if we look at other accounting information, things like the user ID, the group ID, that's defined here. Who owns this process and what group this process belongs to. We have a timeout, we have different priority information here. And if we look further down, we have, see if we can find struct, that's memory management information. We have the signal handlers. We have, let's see if we can find it. We have file system information, all the different links that this links to for file links. We have some swap addresses, so that's if you're going to push this PCB out to disk. We have, let's see if I can find debug registers and so forth. So we have all sorts, here we go, the next task and the previous task. So this task structure, or this PCB, exists both in two lists, a list of all available processes on the system, that's this first row here, next task, previous task, and then here, all of those executable processes. There's another linked list that this can belong to. And so that's the actual process control block or task structure in Linux operating system. So let's go back to the PowerPoint slides. So we're back in the PowerPoint slides, and let's go forward. So I encourage you to take a look at the link. It has a number of key data structures for the Linux operating system. So let's take a look at scheduling. Now, with process scheduling, we said that you're going to switch between different processes to give each one some amount of time on the CPU. And so in order to make sure the CPU stays as busy as possible, you want to make sure that this switching, this copying of data from a PCB to the CPU, and then writing down the CPU status on the process back to the PCB, that has to be really quick. Because when that happens, no other work is occurring. So you want to make sure that the switching part, this context switching as it's called, is very fast in order to spend as much of the time for the CPU executing actual instruction streams. So you want to maximize CPU usage. There's a task in this operating system called the process scheduler. And the process scheduler is that part of the operating system that looks at the linked list of available PCBs or processes and selects from among them. And the one it selects is going to be the one that's going to be executed next on the CPU, i.e. its information in the PCB is going to be copied onto the CPU. And so the operating system maintains a bunch of queues, and these queues determine what processes are available to contend for sharing of the CPU by the process scheduler. So there's something called a job queue, and that's a linked list of all of the processes available in the system. But not all of the processes available in the system can be put onto the CPU. Now, those processes that can actually be put onto the CPU by the scheduler or taken off the CPU, those are in the ready queue. Those are the ones that are active, the ones that are possible to execute. And so we have our ready queue, and that's the set of all processes residing in main memory, and they're available to be executed. So at a moment's notice, if you're in the ready queue, it means that you can be executed. We also have device queues, and the device queues correspond to all of those processes that are waiting for information from some device. Now, that could be a disk device, it could be the network, and because they're waiting, they're not available to be scheduled for execution of their instruction streams by the CPU. And therefore, we have a separate queue called the wait queue, the device queue, and the device queue is associated with each device. So if a process is waiting on the network device, it's in a separate linked list, the device queue for the network. If it's waiting for the disk, it's in a separate device queue for the disk. And so each device queue lists, the linked list, all of the processes that are waiting for information from that particular device. And the processes then will migrate, they'll move from one queue to the next, depending on whether they are waiting for a device, they can be scheduled, or what have you. So this is a visualization of the different queues. We have the ready queue, and as a singly linked list, it has a head pointer and a tail pointer, and you'll see that each process control block has a next pointer. So in this case, process 7, as defined by information in PCB 7, is the head of the ready queue, and the next one in the list is process 2, identified by PCB 2, which is the tail of the list. We have here a bunch of device queues: magnetic tape, another magnetic tape unit 0, magnetic tape unit 1, disk 0, and we have terminal, like a terminal for viewing display visually. So the disk queue, the device queue, has a head and has a tail. It's another singly linked list. At the head is process 3, defined by PCB 3, and at the tail is process 6, defined by PCB 6. And that means process 3, process 14, and process 6 are all waiting for disk unit 0. Likewise, terminal unit 0 is being waited on by process 5. So we have a bunch of processes, and these processes, when they exist in a device queue, that means these processes are waiting for I/O from these particular devices, and it's one queue per device. So this is a look at scheduling. Now we have the ready queue, and we said at the outset that the ready queue list is a linked list, and it has in it the PCBs of all the processes that can be selected. So we start out with the ready queue, and a process is scheduled by the scheduler, selected for execution on the CPU. So it can exit the CPU, and it's done, go to that terminated state, or it can do a number of things. It makes an I/O request, like reads a file. Well, what does it do? It moves from the CPU, it writes down information for state for that process, it gets taken out the ready queue and put into the I/O queue. And so it's now waiting for I/O. The I/O occurs. It's now ready to do something because that I/O device buffer has transferred its data from the I/O device buffer to a memory, and now the process is ready to resume. So the process goes back to the ready queue because now that information that it got from the I/O device is in memory and it's now ready to be scheduled on CPU. Another alternative is an interrupt is thrown because the amount of time the process could execute on the CPU has expired. So what happens? It's taken off the CPU. The current status is written into its PCB. It's put onto the ready queue so that it can be selected again. Now, this idea of picking off the ready queue, scheduling on the CPU, and then sending it back to the ready queue, that gives each process some opportunity to be executed on the CPU. A process could also fork a child. So what happens? It creates a copy of itself, loads a new program, and it now has a child process. That process executes, and then they both go back onto the ready queue. It could also wait for an interrupt. So maybe it's waiting for the network buffer. Well, what happens? It comes off the CPU, waits for the interrupt. Interrupt occurs, it wakes back up. Service routine is done for the interrupt service routine. It joins back to the ready queue and can be scheduled again for fractional usage of the CPU. And so this queuing diagram represents the relationship between the various queues and how the processes migrate from one queue to the next, depending on whether they're waiting for something or if they're available to be scheduled for execution on the CPU. So there are various schedulers in the system. One is called a short-term scheduler, and this scheduler looks at the ready queue. It looks at which processes should be executed next, and it allocates them to the CPU. Allocation meaning that the process control block information is populated on the CPU, and the instruction stream is resumed or initiated. Sometimes in simple systems, it's the only scheduler, and the short-term scheduler is invoked very frequently on a millisecond time horizon because it's switching very rapidly between multiple processes on the ready queue. So that's how the sharing of the CPU happens. And of course, once your time slice or your period of time is over, your status is taken off the CPU, written into the PCB, and then you join the queue at the tail again. You also have the long-term schedule, and this is sometimes called the job scheduler, and this one decides or selects which process should be brought into the ready queue. Now, of course, this is not done as frequently as the short-term scheduler, and this long-term scheduler controls the notion of the degree of multi-programming. Now, the degree of multi-programming talks about how many processes can exist for availability to share the CPU. And so you can have maybe, let's say if you had 100 processes, but only 200 of them, rather, if you had 100 processes and maybe only 20 of them or 30 of them are on the ready queue, what this long-term scheduler does is says, okay, I'm going to even increase further beyond 30 the number of processes that can contend for the CPU. And so the higher the degree of multi-programming, the more processes are available on the ready queue and therefore sharing the CPU. Now, this long-term scheduler is not invoked very frequently because it can decide out of the 100 processes that I have, only 30, maybe 40, maybe 20, maybe 10 are going to actually contend and i.e. share the CPU. Now, a process can be described as one of two different, and sometimes it's a mix, types of computations. One is called an I/O-bound process, and these processes spend a lot of time doing input-output operations. So maybe you have a process that's always reading and writing to and from disk, like a database. You're going to read a lot of stuff from disk and write a lot of stuff to disk, but you're not going to spend a lot of time running arithmetic operations or floating point operations. They make heavy use of I/O, and as such, that means they're going to be waiting a lot. They're going to be sitting in device queues, spending most of their time in device queues. Then you also have the converse, which is CPU-bound processes, and these spend a lot more time doing computations, like a lot of floating point, a lot of arithmetic operations. Now these spend most of their time executing instructions on the CPU, and so you're going to have a small number of long bursts on the CPU, meaning executions. But for the I/O bound, you're not going to spend a lot of time on CPU, a lot of very short periods of time on the CPU, short so-called CPU bursts. And so what the long-term scheduler strategizes on It strives for having a good mix between I/O bound and CPU bound. Because if you have more CPU bound, you're making more use of the CPU. I/O bound, they don't use the CPU very much. And so if you try to mix them together, you're keeping your machine usage balanced. And so there's also something called a medium-term scheduler. And this medium-term scheduler can be added to the long-term and the short-term if the degree of multiprogramming is too high and you need to make it smaller. And how does it make it smaller? Well, it selects some processes from memory and it stores them temporarily on disk. And this is called swapping. Now, this process control block we said is stored in memory, but it can also be written out to disk. And there's a special place on disk called the swap file or the swap disk or swap partition, which is set aside for storing process control blocks. While yes, it's slower to store it to disk and remove it from disk, this is done in service to trying to make sure there aren't too many processes sharing the CPU, because if there are too many sharing the CPU, everything slows down to a grinding halt. And so this idea of swapping is taking these process control blocks out of memory and storing them temporarily in disk, because you can store many more on disk than you can in memory. Memory is much smaller than disk. And so you start out with a process in the ready queue. So here we have process arrives in the system in the ready queue. It's scheduled for execution on the CPU. And let's say it's waiting. It joins the device queue. It's waiting for I/O. The I/O finishes, completes, goes back to the ready queue. It can also, when it's on the CPU, if the degree of multiprogramming is too high, it gets swapped out. So what happens? It comes off the CPU. The information for the status of that process is written to the process control block for that process in particular or of interest, and then it's written out to this swap space on disk, this special set aside place on disk. So then after some period of time, it says, hey, well, this hasn't really executed for a long time. Let me increase the degree of multiprogramming and bring it back into memory. It's swapped back in so that PCB is read off a disk, back into memory, put back on the ready queue, and now can be available for scheduling on the CPU. So then, lastly, it can execute and then exit. It's now in the terminated state, and in the terminated state, it's no longer on the CPU. All right. So multitasking in mobile systems can be a tricky thing, and this multitasking, some early versions only ran a single process at a time, and while the single process was running, all other processes were suspended. Now, due to screen real estate, many of these user interfaces limited, like early versions of iOS, it limited what you could do, and it's provided for only a single process in the foreground that can be controlled through the user interface. And the idea was, hey, well, okay, I can only display one application at a time on my interface, so I might as well only run one thing on the process in the foreground, and the others were suspended, not doing anything in the background. So then what happened, in addition to this foreground process running, you had multiple processes that could run in the background, but they just didn't have a display, and they were very, very limited. And these limits included that they're only very short tasks, like getting notifications for events and things like playing music, things that were very low bandwidth and didn't use a lot of resources and simple ran in the background. In Android, remember Android is based on Linux or Unix, and it runs in the foreground and the background with fewer limitations on the background processes. These background processes in Android, it is written on Linux, built on Linux. They use a service to perform the task. So a service doesn't have interface, and it runs in the background even if the process is suspended. So any process that needs to make use of certain parts of the system would make a call through a service that's running and up and available, and the services don't have any user interfaces and use a lot less memory. So you'd have these low memory processes running in the background or services, and any process or program that wanted to use it would just pass it data, and the service would perform that task on behalf of the process. So our context switch is the name of that storing information in a PCB when you kick a process off the CPU, and the reading of that PCB information onto the CPU when you're going to switch to another process to execute on the CPU. So when the CPU switches from one process to another, the state must be saved for the old process, and the state for the new process that's going to execute gets loaded. And this is called a context switch. And this context is the executable status of the program, of the process, program and execution. And so this context switch, it's overhead. When we saw the task structure in Linux, we saw all that information. It takes a little bit of time, not a lot, but a little time, non-zero, in order to do this transfer, both the reading or the writing of the PCB information, the task structure, either from the CPU to write to the PCB or to the CPU to read from the PCB. So this takes time. And during that time, no other work can happen because the CPU is busy doing this through the operating system. And the more complex the operating system, the bigger the PCB and the longer the context switch. So if you have a very complex operating system, your PCB stores more information. It's going to take more time to do this reading of the PCB onto the CPU or the writing of the PCB from the CPU. And so this is dependent on the hardware. And so some hardware gives you a bigger register file and more information on the CPU. And sometimes some CPUs allow you to load the context of more than one process at a time. Certainly multi-core systems allow you to do this. Okay, so we're going to end there, and we will pick back up on Thursday. Until then, please make sure you're doing the reading. Please stay healthy and stay safe. I will be releasing the first programming project. Please look out for that and get started on it right away. So with that, stay healthy, stay safe, and I will see you Thursday.